right, so let's start this very important topic, which makes a huge amount in difference in good projects, good quality projects, and projects that fail miserably. I usually take the image to say the difference between a project that is really successful and a project that is giving extremely bad results is usually you have a continuum of project between these two sides. That would be the bad project and that would be the good projects. The project succeeding nicely and the project failing miserably. There is not a single nice little lines which go from one to the other. It's actually very different. It's either it succeeds nicely or it fails miserably and has very bad accuracy. It's very, you will not very often find intermediate results where you have a project which kind of processed but not very well. And one of the main important aspect of this is the flight plan, how the images were captured, the way the camera, but even more important than the sensor by itself is really how were the images captured one after each other, in which geographical space, in which orientation, to ensure a maximum of overlap in all the images in the whole project. And that's basically going to be the topic of today. To do so, I will start first with an introduction to modern photogrammetry to just get the concepts right, what we're talking about, and to really, as everything is so depending on the matches and which drives the overlap of the images, this is very important. Next, we'll go a bit more concretely for projects which are nadir. Basically, this is a huge amount of projects, mostly by fixed wing. And I'll discuss also of all the tricks and the possibilities with oblique projects. And I will also present quite many use cases of actual projects to have an understanding of what's possible and how to do it. So let's start with the introduction about modern photogrammetry. So Pix4D Mapper is a software that's able to transform simple 2D images into 3D results, such as point cloud, a digital surface model, and also an automosaic. And to understand that, we need a little bit of understanding of what's a camera and how can you recover what you have lost using processing of images. So a camera. When you take a picture with a camera, you are capturing 3D world, but you are losing information when you take a picture. You're transforming 3D to 2D. Not only you are losing this information, but things are changing in the picture. Objects which are very far away will appear very small. Objects which are very close to the camera center will appear very big. So when you take a picture, many things happen. The most important one, you are losing information about the distance to the object. And the second important thing which is happening is that not only you're losing information, but in addition, the object will change size depending to the distance to the camera. Now, this is what basically is called perspective. The good news about this is that if you move the camera to a different location, the objects you will have not the same distance toward these objects anymore. Let's say you have the easiest way to understand is as you have two eyes. It's like if you had two cameras. If I put my finger in front of one of my eye, it will be very close to it. But if I look now with the other eye, it will be further away and the object will have a different size. So what the brain is doing is that it's going to compute the difference of size between these two images. And by computing the different size, it's able to basically triangulate the object and compute back the information in depth, which basically gives you back the 3D information. And this is exactly what happens in Pix4D Mapper. You have multiple images taken by a single camera at different time of the world. However, the main hypothesis is that most of the items in the images do not move, like buildings, trees. These objects will not move through the course of an image acquisition process. So if they don't move, the software will basically analyze the object, the content of the images, and by checking the difference, we're able to triangulate to find back the depth. Now, to be a bit more specific for the real process which is happening into Pix4D Mapper, an image will be, so this would be a standard 2D image taken at two different locations. The first step the software is going to do is to check for key points. Key point is basically an interesting place in the image. Let's say in that image, it could be the corner of this building. If you know the camera model, which is basically how the perspective affects this particular camera, you can draw it more or less as a pyramid, with the center of the pyramid, the top of the pyramid, being the center of the camera. By shooting a ray from the center of this camera to the key points that you have detected, and if you repeat the same in a second image with the same key points, with the same location of the object, you can basically shoot these two rays and triangulate and get a 3D point. For that, as I said just before, you need to know the camera model, and basically camera model means the focal length, the principal points, and how the lens distorts the image. And you also need to know the external orientation, which is basically the camera position and the rotation. And something very interesting about Pix4D Mapper is that it's able to compute a precise camera calibration and relative model from image content only. What I'm saying there is that there's so much information in the images that without any other additional information than just the pixels of the images, you are able already to find out and to recompute, to re-estimate all the parameters of the camera, meaning the interior, meaning the focal length, the exterior, the orientation between each other, and generating at the same time a 3D representation of the whole model. And this is done in three main processing steps in Pix4D Mapper. I'm going to mostly talk about the initial processing. The initial processing is really the steps which is going to estimate by itself automatically all the external and internal orientation of the images. It does that by computing key point extraction, matching them, doing a camera model optimization, and geolocation. This webinar is not really focused on the next two steps because the flight planning is mostly going to impact the first step. Let's go a bit closer into what we mean by camera calibration, what happens during the first step of Pix4D Mapper. The very basic step which is going to happen is key point extraction. As I said earlier, the software is going to detect to try to, the software is going to try to find automatically some interesting areas in the image. We will see it a bit later when I open Pix4D Mapper, what are key points, what the software understands as key points. Let's say just for now, it's interesting places which can be recognized, and on the seventh step, which can be matched across several images. So if you have two images taken from different locations, you should be able to say that the corner of this building here is the same as the corner of the building in the second image. To give just a scale of how many key points we are talking about, in a typical 14 megapixel image, you would find the software would extract automatically around 60,000 key points per image. Then when it does the matching, the software will try to match with neighboring images to find if there is relation between the images. And usually after this process, you will get an average of 6,000 matches per pair of images. This depends on many different factors that I'm going to talk a bit later on. After finding matches, there could be many wrong matches and many correct matches. The software is going to try to orient the camera in 3D with respect to each other by using the matches and by using an initial guess of how the perspective is working in this camera. It will do it in an iterative way. By that I mean that it will start first with 2 cameras to try to put them together. As soon as it found something reasonable, meaning that when you triangulate your key point matches, you get most of the matches are reprojecting at the right place, meaning that they've been validated. You will try to add additional images, and each additional images will validate more matches, and by validating more matches, we'll be able to better optimize the focal length, the lens distortion, and the principal points of the internal and external orientation. After doing this step, after growing gradually and optimizing for all the cameras, the software will then use information that you have added also, which could be geotags or GCP, and it will try to fit the model to these geotags in GCP, and this is the step which usually gives the geolocation of the process. The good news is that everything is fully automated, so there's nothing you have to do. If the data is of sufficient quality, the whole process will happen automatically, and all the images will be matched against each other, computed, and the whole 3D will appear. And that's maybe a good time to make a small parenthesis with regard to traditional photogrammetry. In traditional photogrammetry, the camera that were used were of very high quality, and most of the time the images were exactly nicely looking downwards. Moreover, we would have very good accuracy on the GPS and on the position of the images. In such a model, you would only need, and this is what happened in traditional photogrammetry, a few Tiepoints per images. Let's say a few dozen of Tiepoints per images, which is enough for if you are in a traditional photogrammetry context, which means a good camera, good GPS, good IMU, good sensor, and very high altitude. This is generally enough. And this is a big difference with the new modern photogrammetry that Pix4D Mapper is doing. In our technology, we are trying to compute as many Tiepoints, as many key points which will produce Tiepoints as possible. The good news about that is that it allows Pix4D Mapper to model and to estimate many more parameters than traditional photogrammetry. One of these parameters is a small consumer-grade camera. We can estimate most of the defects versus traditional photogrammetry of these sensors, meaning the internal geometry is always changing as soon as you have shock or temperature changes. We are able also to model imperfection in the lens, which is doing radial distortions. And we are able to compute 3D without starting from an initial guess about the position and the orientation of the camera. The trick that is used to do that is by having a huge number of tie points and key points. As I said in the slide earlier, we are using around 60,000 key points that we extract per images. When you have 60, and this is basically what I represent in this image, here you would have two images. This would be the first one, and on the right you would have the second one. If you were able to extract 60,000 key points in the first image and 60,000 key points in the other image, the likelihood that you have many good matches is very high. And very often you will end up with thousands or tens of thousands of matches. By having so many matches, we are able to constrain much more the model, to be able to model most of the imperfection of consumer-grade camera. And in addition, this would be a side view of a project. The images would match nicely to each other, and you would have almost no error accumulation. Error accumulation is, let's see in the second example on the right, is, for example, if your images didn't have a lot of overlap, there would be only a few points which would tie these two images together. If you only have a few points, if you have a slight mistakes in these points, this could make that you would slightly start having an error in the orientation of these two images. If you start having a small error, it could, and let's imagine the error would be here, even a slight error in angle will affect all the other images, and potentially you can have very large distortion in your altitude when this effect starts to happen. And what we found out is that with consumer-grade camera, a rule of thumb is that if you have in average, in minimum for each pair of images around 1,000 matches, the error accumulation will be almost insignificant, and the whole project will calibrate, and the accuracy of the whole project will be extremely high. And again, with a camera in the range of 20 megapixel, this usually accounts for an overlap of 75% between each images. So let's summarize. If you can compute, by computing a huge number of key points, we are able to modelize a lot of imperfections and to correct for and to have very good results with consumer-grade camera. But this works only if we can find enough tie points between images. And to find enough tie points, the parameters that affects the most is the overlap between the images. And to relate a bit to the title of this webinar, which is Optimal Flight Plan, an optimal flight plan is really about getting enough matches. And by getting enough matches, your project will be of high accuracy. So there are several factors which impact what I just said before. Enough matches in our language means usually you need over 1,000 matches per image pair. However, it depends on overlap, as I just said before, but it's also going to depend on the image size and on the visual content. So let's say you have a tiny camera, a camera of 600 times 800 pixels. Very likely you will not be able to extract 60,000 key points from it, but only maybe a few hundreds. And if you can only extract a few hundreds of it, it's going to be very difficult to have 1,000 matches between pair of images, which basically means that larger megapixel will help to get more matches with a normal overlap. Or let's state it differently. If you have small image size, then more overlap is required to have a sufficient number of matches. The other thing that affects is visual content. In the images showed previously, there's a lot of visual content. You could see a building, and there are lots of edges, lots of texture, lots of interesting places. However, let's say that we are in Antarctica and we are taking a picture of full snow, and there's not a single variation in texture or nothing, then the visual content is very low. And per image, even if there are 40 megapixel or 60 megapixel, you will only have very little amount of visual content. And in that case, the way to get the right number of matches would be to have more overlap. And as just stated before, empirically what we've seen is that with images of 12 megapixel, we would recommend to have something in the range of 75% overlap. But I'm going just to talk about this right now. So let's go a little bit more in understanding what is a key point and how key points affect the whole calibration. What do we mean by good key points, bad key point? What is a good image and a difficult image? So in the first process of calibration, the very first step is about trying to extract as many key points as possible. It's not very intuitive to understand what makes a good key point and what does not make a good key point. This is something that, however, you can learn by watching results in Pix4D Mapper to get a better feeling of what it means. But here we can already give some very good guidelines. In general, good images are rocks, bushes, dirt, building areas, man-made structure, urban areas. These are usually places where you have a lot of texture and interesting content. In addition, we usually recommend to do any type of processing with images with more than 10 megapixel. If you have all of this, it's very likely that per images you will extract at least 10,000 key points. What is then, in contrast, a difficult image? A difficult image would be sand, snow, fog. Basically, that's what you can see on the right, where you have very little contrast in the image, meaning very little places where a key point can be extracted. If you have blurry images, this will also impact and have lower accuracy, lower number of key points. If you are overexposed or underexposed, this will also greatly reduce the amount of key points that can be extracted. However, just as a tip, if you had to choose to be slightly overexposed or underexposed, we would recommend to be slightly underexposed, as you can still get a few more features by being underexposed than overexposed. With very, very small images, such as less than 3 megapixels, this becomes also very difficult to do computation of matches. And in that cases, you will maybe extract less than 100 key points, which is enough for Pix4D Mapper to process, but you might get slightly less accurate results, and I will explain how to detect that and how to correct it. Now, if you remember in the first slide, in one of the first slides I showed, it was extracting key points, but then it was about matching key points. And there are some scenarios which you can extract a lot of key points, but which are then very difficult to match. And if they are very difficult to match, then you still will not get many tie points at the end and not many validated matching points. So let's see what's easy to match. If you have an image with a huge number of key points, very likely this is very nice, and you will be able to match a lot. And again, with high overlap, the more overlap you have between your images, automatically it will increase the number of possible points that can be matched. What's harder to match is when you have indeed very low number of key points per images. When you have, for example, trees at low altitude, but this I'm going to talk later with some examples about it. When you have extreme angle, so that would be the tree at different altitudes, which looks very differently. Or when you have extreme view angles or very low overlap. And then there are also some places that, even if you extracted many key points, are impossible to match. And that would be, for instance, water. If you have water, water is a reflective surface, which means that the texture will change with the position of the camera. And this does not validate one of the main hypotheses we did at the beginning. And this will not, you will not be able to extract any information from reflective surfaces or surfaces which are constantly moving, like if you have waves on the water. Now, just as a small apartheid, if you have only a few number of objects that have been moving in your images, this is all right, because in an image, let's say that you have 60,000 key points. If you have a few cars moving, maybe a few key points will be extracted on the cars, but that's only 100 key points out of 60,000. So it's very likely that the software will be perfectly able to handle this situation and still calibrate nicely your project. In fact, we did some mini experiments, and you can have up to 60% of your image which is not good content, like potentially water or moving cars, and the image will still be able to use the 40% of the image which is not moving and which is where you can find nice matches to calibrate the project. So let's go in more concrete examples about flight plans. Here we usually see really two different types of projects. There is the aerial nadir type of projects where you would fly in a grid. This is where usually you're interested in the automosaic, in the DSM. The point cloud will also be good quality, but this is really project where usually you use a fixed wing and you cover larger surfaces, and your goal is to really produce maps. Another scenario where you can also use the software, which is slightly different, is when you try to do purely oblique imagery. And this is when you try to achieve single object reconstruction, buildings, and where in this situation the optimal output will be the 3D point cloud, because you will have points on the facade and everywhere because you've captured it. Of course, you can also mix the two types of projects, and I'm going to discuss about that at the end of the presentation. So let's go first in the regular flight plan, where basically you fly optimally in a grid, where the main purpose is to have an homogeneous spacing of the images. This would be the best, the most optimal way of distributing images in space is by taking them at equal distance in each direction. However, you can also give a lot of different type of if you don't do this in an optimal homogeneous spacing, it will also work, but you may get slightly either less quality or slower speed or less reliability. So it might happen more often that you have some mistakes when you do the processing. So let's talk about the optimal one, where really you try to, the images are taken with as regular spacing as possible. You normally put your camera in such a way that the large side is in the same direction as your flight line. The reason is that even though we would try to make a perfectly nice grid, usually your flight time will depend on the distance. So you will want to reduce the distance you do, and the best way to reduce the distance is to make these lines as wide as possible. So in that respect, to make the lines as wide as possible, to increase the amount of surface you can cover and to maximize the speed at which you acquire the images, what we recommend is to put the camera on the same direction as your flight plan, and to have a bit higher of frontal overlap so you can reduce a little bit the side overlap. And usually as settings, it will depend on many factors, but 70 or 85% frontal and 60% overlap on the side is something which is really, really recommended in most of the settings. If your overlap is too low, meaning basically that the images between each other are too far, you will have a lower number of matches, as I explained before. And if you have a lower number of matches, you may, it will not happen every time, but you may have more error accumulation and or wrong estimate of internals. And this may start making either bending effects in your project, or as I showed before, you may start having some error accumulation, meaning that if you try to measure, you may be a few meters off at certain areas, or it may just not even calibrate the project. Now, it may also happen that the opposite can be true. If your overlap is too high, meaning that your images are too close to each other, it's another effect which is happening, which is what we call short baseline, which I talked in another webinar called about the ray cloud, where you have more information about what is short baseline. It has two effects. First, it's going to make your computation much more slow because you have too much matches to compute, and it may also increase error accumulation. Now, just to make clear, when I talk about overlap too high, this is most of the time when you are taking pictures at the same location multiple times, maybe just shifting a few centimeters. This is when you have over 99% of overlap in images, where you may have this type of effects happening. So just to summarize, the best flight plan for Nadir project is in a grid. You have frontal overlap of about between 70 and 90%, possibly never lower than 70% and never higher than 90%. Nice spaced, and you can also slightly space out the side overlap by making sure that you increase a little bit the frontal overlap. And this is a question which comes very often, is how to compute the overlap percentage. This is usually what is done through your UAV or your manned aircraft ground station. The overlap between images is something that will depend on several factors. One of the factors is the altitude at which you fly. The higher you fly, the more distance you cover on the ground. And you can see that at low altitude, the spacing of the images needs to be much closer to each other than at high altitude. The other effect is not only the altitude, but also the focal length. if you have a camera where you zoomed a lot, so it means with a short focal length, high focal length, you will only cover little space on the ground as if you had one with extremely large focal length. So you can find on our support website the mathematical formula to exactly compute from your specific camera and fly altitude how much overlap you will have or in any direction. All right, now this is all good, the theory. In practice, how can you check how much overlap was actually really done in this project? And we offer 4 different ways to check of the overlap in your project. 2 of them are in the quality report, the overlap and the matches figure, and 2 of them are by checking the ray cloud. So let's open a project. In this project, you can see that there's about 100 cameras, and you can see that the spacing between each images is very regular. So the distribution of the image in space is quite homogeneous, which makes the processing fast, reliable, and accurate. In that case, the overlap was set in this UAV ground station at around 70%. In the quality report, which I'm opening right now, where is it? There. In the quality report, you can see a few interesting figures. Let's first check the overlap figure. This figure will let you know about the number of images which are basically seeing these 3D points. In green is when you have more than 5 images watching this point, which usually represents something like 70% overlap. In yellow, only 3 cameras are visible from this point, which basically means that the overlap is more in the range of under 50%. And in red is when you have less than 2 cameras in this area of the reconstruction. You can see 2 very interesting factors. One is that, okay, this dataset is mostly good, but on the border of the dataset, you will all have less overlap, and this for 2 reasons. Reason number 1 is, obviously, if you're in the center, this point will be seen by all the cameras on the surrounding. However, if you are in the edge of the project, you will just automatically have less camera which can be visible from there. Another factor is that this dataset is not flat. This dataset has actually quite some altitude change. And as the overlap depends on the altitude between the camera and the ground, you will have actually a much higher overlap on the bottom of this query than on the top of this query. This can be visualized in the report, where you can see that, let's look it on with the same perspective. You can see that on the edges of the query, which are much higher, the overlap is also much less because the distance between the camera and this particular place of the ground is also much less. This is the first way where you can understand how much overlap you have in your project. And the overlap will depend on the terrain shape and on the spacing between the images when you take them. There's another figure in Pix4D Mapper that helps you to understand if the overlap was sufficient to get high quality results. And this is the 2D keypoint graph. In this picture, you can see the same area from the top as in the previous one, but the software will draw a connection between each camera that have matches. And the darker the connection, it means the more matches there are between these two images. What you can understand from that is in this area, you have an extremely large number of matches between the images. If you have, and this basically means that your overlap was sufficient regarding the quality of your visual contents and the size of your images. You can also see that on the border there, it's slightly more bright, meaning that there's less matches. And this is very likely because it's on the border of the reconstruction, so you have automatically less images, and also you are at a higher altitude. This would be the two ways to visualize it from the quality report. Now, in addition, you can also use the ray cloud to visualize the distribution of automatic tie point in space. Let's open another project. Let's open this project. In this project, you can see these are the automatic tie points. And you can see that in some areas where you have high level of texture, there's a lot of tie points generated, which basically means that there was a lot of overlap between these images. However, in some other part of the project, you can see that there's a very, very low number of tie points generated. In that case, let's open the quality report. The overlap is good. All right, so the images we're taking with the right distances between each other to keep something like 70% overlap between each images. But something important to notice is that the visual content is not always the same in the whole project. And in this specific project, you can see that very likely there's less visual content on the bottom here than on the top. Let's look at the images. On the bottom, you have nice texture. This is a field with a lot amount of contrast, and this can be used to generate tie points automatically. However, on the top of this field, you have trees which are taken in a very blurry way, and visually it's indeed very hard to see that there is to extract matches from that. Moreover, this is the very specific examples of tree at low altitude. When you have trees and you are taking them at very low altitude, on one image you will have one side of the tree, and the other image you will have the other side of the tree. And this cannot be matched together. The workaround for that would be to either increase the overlap in this specific area or to fly at a higher level, at a higher altitude. So in this example, you can see that the overlap was sufficient for most of the bottom of this project, but the overlap was insufficient for this area. And the reason is because the visual content is much more complicated. And by being more complicated, it's less easy to match. And if it's less easy to match, you need more data to still have enough matches. Another way to visualize, to have a better understanding of this tie point is by clicking on camera in the ray cloud. Let's select this camera. By clicking on camera, you will have this interface opening up, which shows you all the little red, orange crosses is a tie point. And you can see where the software is computing most of the tie points. It's in places where you have nice contrast. However, trees at high altitude, for the same reason I just explained before, will have more difficulties. You can filter on the right the number of matches for each tie point. If I put it there, I will know that all these tie points have been matched in 19 images, which means that it's a very strong tie point. In this case, you can see that even by sliding, sliding with the cursor, the tie points are very well distributed along the whole image, across the whole image. This means that very likely it's a very well calibrated image. If we go above there in the corner and you click in this camera, you will see that there is first much less number of matches. And in addition, the distribution of this match is not well equilibrated along the whole picture. They are mostly in only one area. If they are mostly in one area, it means that potentially the image has a bit more freedom in the way it's going to calibrate and the way it's going to orient itself. And this is a very good way to see where there is potentially accumulation of error. In this image, you could very well have all this area which is going to accumulate error. However, in an image where you have tie points covering the whole surface, it's very unlikely that there's any accumulation of error happening. So this would be the four recommended way of estimating the overlap in an image. Now, let's see a little bit more different use cases of what can go wrong and what we see mostly the uses where we see problems in the processing and where do they come from. One of the reasons sometimes calibration fails is when you have camera type, when your camera is of very low resolution. Let's say you have a 1 megapixel camera. In that case, you need to increase the overlap of above 90% to have results more reliably, because you have, as explained before, you have very little number of key points, meaning very number of matches. So the only way to increase, to have a good number of matches, is to increase the overlap. If you have a slow rolling shutters camera, this is many of the video camera or this type of camera. Basically, there you have to both optimize, you have to use an option in the software which is called optimize externals only, and to use in the software the alternative processing pipeline. Maybe I can quickly show this example. When you create a project, you can choose between 3 different options of processing. By default, you should choose Arial Nadir. However, if your camera is is of lower resolution, or has rolling shutter problems, or alternatively the image content is very low, you should check this alternative processing mode. And if you have good geotags and accurate georeferencing, then the software will still be able to process your project even with a much lower number of key points. So if this type of things happen, increase the overlap and try to use the alternative processing mode. If you have blurry images in your project, if you have less than, let's say, between 5 and 10% of blurry images, the software will handle it quite nicely and will automatically discard the wrong ones and take advantage of the other one. However, if you have more than 10% of your images which are extremely blurry, we would recommend to remove them by hand before starting the processing. Terrain types. So as the examples I showed before, if you have some very difficult terrain types, either to detect key points or to match, so that would be the snow, when you have fog, sand, or very repetitive pattern like fields, farming fields, the first thing we would recommend is to use our alternative processing pipeline. It requires better geotags, but if you have good geotags, you can really use this alternative processing pipeline to get much more reliable results even with difficult terrain. If you cannot use this alternative pipeline because you don't have geotags which are good enough, what we recommend is for this type of terrain to increase the overlap. If you have multiple terrains type in the same project, and that's exactly like the examples I showed before, in this example, the overlap was really sufficient for all this area, but was not sufficient for this area there because it was not grass and nice little pathways. It was only forest at low altitude, which is much more difficult to extract key points from. If things which can go wrong, that's even by respecting this nice flight planning, if your camera is heavily over or underexposed, this will also reduce the number of key points, and by reducing the number of key points, you will have less matches, and less matches meaning more problem. So we would really recommend to fix correctly your camera settings to make sure that you have the best type of imagery as possible. Something which may go wrong also is if you have geotags, but your geotags are for very, very low accuracy, or that the synchronization is not happening correctly. In that type of projects, you will have more success by removing the geotags. And we have an option in the software when you create a project to clear all the geotags. You will have, the software will better reconstruct without geotags than if you put geotags which are extremely wrong. And by meaning very wrong means usually when you have more than, let's say, 50 meters of inaccuracy in your geotags. Another thing, another big important factor is illumination changes. If you have illumination which is changing in your project, this usually does not have too much impact on the calibration and on the point clouds. The accuracy, the software is very, very good at compensating for difference of illumination in different areas. However, your automosaic may have some artifact if the change of illumination is too severe between different images. So what we would recommend there is make sure that the settings again of the camera are set in such a way that you don't have an image which is going to be extremely bright and extremely dark next to each other. However, if you have illumination changes which are providing moving shadows, there you may have much stronger problem. But this happens only in very specific cases. And most of the time where it's happening is in mining environments. In mining environments, you will have in your terrain a lot of little rocks everywhere. And rocks will do each of the little rocks will provide a shadow. Let's say that you do a flight in the morning where you have all the shadows, very large shadows going in one direction. And then you fly again in the afternoon, you will have shadows going in the other direction. When you try to merge these two projects together, many of the key points will be located between the edge of the object and the shadow. And as they have moved between your two projects, this may cause several problems during the calibration. And one way to solve it is to use manual Tiepoints to make sure that the two projects are not merging on the shadows which have moved, but on all the rest of the content. From experience, we have seen this type of issues happening basically only in mining environments when you have huge difference like morning and afternoon. In most of the other environments, like a city or urban areas or even in forests, this is usually not happening, because even if you have shadows which are moving, there will be only, let's say, 10% of the content of the image which is represented by shadows. And 10% the software is good enough to actually make sure that this is not consistent and to take all the other information. Only in areas where most of the image is actually done from shadows, and this would be really in mining environments where you have tons of little rocks everywhere, where this happens. The best way to solve this issue would actually to fly simultaneously all your different flights, so you don't have shadows from the morning and shadows in the evening in the same project. You will have everywhere the shadows of the morning. Another effect, which I already talked a little bit before, is sometimes it happens that you have too much perspective. Too much perspective could be, for example, trees at low altitude. This will happen when you have when you are taking images at low altitude of a forest, and you look at the images, you will see that even at 80% overlap, one image will only picture one side of the tree, and the second image will only picture the other side of the tree. And in that case, there's no way that we can match one side with the other one because they don't look the same. And there you have two tricks to solve this type of issues. The easiest one is to fly at slightly higher altitude. By flying at a higher altitude, you will have much less this effect of one image one side of the tree and the other side. And you will have less perspective, meaning that you will be able to match many more features between the different images. The other way to solve it is, if you cannot fly at a higher altitude, is that you need to have a massive amount more of overlap, and this is usually can be up to 95% of overlap for this type of datasets. In general, it could also happen when you have too much. This effect of having too much perspective is when you have images that are from the takeoff, from the landing, on when the fixed wing is turning and taking images really almost totally oblique. If you have one oblique imagery in a ton of different nadir images, the angle between the camera is probably too high to match features between them. And this may, most of the case, this will be handled nicely by the software, but it may add some confusion. So if you have a project that fails and you have images of takeoff, landing, or of the turns, You can try to remove them, and this will very likely improve the quality of the reconstruction. Another important topic is altitude changes in terrain flights. So Pix4D is able to usually support up to 2 times changes in altitude. And maybe this is more easily explained in this graph. Let's say that you have, this is a side view, this is the terrain, and this would be different flights that you do. In this flight and in this flight, if you want them to merge together nicely, the difference in GSD, in ground sampling distance, if you have a ground sampling distance here of 4 centimeters, here for the same area, it should be not more than 8 centimeters. Of course, the software is able to handle it very nicely, and very often, even at higher altitude changes, you will have good results. But in general, to avoid having problems, we recommend to stay within this two times GSD boundary between flight lines. A good example for this project would be this data set. In this data set, you have around 1, 2, 3, 4, 5 flights which have been done at different altitude because the terrain is changing altitude. If you look at the distribution of Tiepoints, it's pretty uniform, but there are some areas which are missing a little bit of Tiepoints, which potentially means that there are problems there in terms of altitude versus overlap. So let's look in the quality report. So in this project, we can see the different flights. We can see that most of the time in the project, the overlap is sufficient, except in a few areas over there, which is exactly the areas which is described there, where the overlap is not sufficient. In addition, by looking at the key point graph, you can see that most of the places the calibration went perfectly well. However, if you look a bit more closely, you can see that here, in this specific area, there are much less matches happening. So let's have a look in the project. Why is this? Where is this happening? So the places where you have less matches is the places which is around here. If you look at it in 3D, this is exactly at the location where you have a huge altitude change between the 2 flights, which is all right when the terrain is pretty low, like here. But in the corner over here, you have a multiple factors which are acting together. The first one is that the difference of altitude is high between the 2 images. Moreover, the altitude between this camera and the terrain is also very low, because right there's a little hill. This may add, in this place, there's a possibility that there is error accumulation happening. To make sure that there is no error accumulation, or to prevent it, the best way is to add a few manual Tiepoints in this area. And by adding a few Tiepoints, you can assess and control if indeed there is some error accumulation happening. All right, let's go in other type of flight plans. That would be for more oblique imagery. Something important to notice is that the overlap depends on the size of the object and the distance to the object. And you have some different type of problems which can happen versus the traditional nadir type of projects. And one key aspect when you are very close to objects is that cameras with large field of view, like a GoPro is the extreme example with like a fisheye camera lens, make the whole calibration more simple. What we recommend for when you want to do purely oblique of a single object is a flight plan such as this one, where you take images of an object in a circle, and the way to know how much overlap and how many pictures is basically every 10 degree an image is taken. So in this project there is 36 images, as they were taken with each 10 degree angle. One trick, which is, so this would be the correct way of doing the most, in our sense, the most optimal way of doing an oblique project. When your object becomes a bit more complicated, you can also, as we show in this example, do multiple of these circles around at different altitude and with different camera angle. The most problematic thing that may happen in oblique projects is when there is too much angle between two images. Meaning basically that you have in this project, in the house project, if we would have only done images every, let's say, 40 degree, you would have these two cameras there. And if you look at the content of the images, the software would not be able to match, would very likely not be able to match directly content from this image from an image which is taken at almost 90 degrees from it. However, the trick to make it perfectly work is to have images in between. By having images in between, the software is able to track much better one feature across multiple images. So for oblique, the main important thing is to have a lot of overlap. And to have a lot of overlap, usually the best is to have the largest number of images as possible. However, and that's also the thing I just said before, one very good trick to have more overlap between images and less problem with these angle differences is to use a sensor, a camera with a very large field of view. And this would be, for example, a camera with fisheye lens, like a GoPro camera. Another topic is about the sky and the sun. In oblique imagery, this can be very, very tricky. Also an example to give a bit more understanding. Test. In this example, we have the reconstruction of a tower, power tower. But there are some images which contains images from the sky. The sky has basically no features. So as soon as your oblique imagery starts to be too oblique and contains a lot of sky information, all these pixels are wasted because there cannot be any features computed on it. So the more your camera is watching the sky, the less features will be able to be extracted from this image. So one trick is always to keep images facing a little bit more down, so the software can use the ground to compute also features, and not just the content of the tower of the object you are trying to reconstruct in the middle. Another thing which is happening usually when you have for oblique imagery is because of this, for extreme oblique imagery, is the sun will very likely have effects on your illumination, and you will have images which are extremely dark and images which are extremely light if you don't adjust correctly your the sensor settings of your camera. So if you don't do that, you will have also many problems. And basically, they are either you take care really that the illumination is constant in all the images, or you need to add more images, and maybe more than every 10 degrees, but maybe every 5 degrees if the sun is too low in your dataset. Another problem, which is also very often happening, is when you have image taken at the same position. This may accumulate error, and if you have too many of them, we would again suggest to manually remove them. So this is most of the tips for the best type of oblique flight plans. There are some additional flight plans which I can also give a few best practice for. This would be for corridor mapping. This is when you have you need to map an oil pipeline, a gas pipeline, very long objects. You can do it by flying only one line, but of course if you fly only one line, you can only have matches between frontal and not between side. So you will have much less number of matches between images just because of that. And this makes it much more tricky and much less reliable. That's why we really recommend for corridor mapping to have possibly 2 flight lines. This will increase by a huge factor the reliability of your project. In addition, if you have only one line, if all your geotags are aligned, it will be very difficult for the software to compute the right orientation of the project. And there you might want to add geotags or GCP to have the right orientation of the project. There is also the possibility to combine aerial and terrestrial, so basically nadir and oblique imagery in the same project. You can do it 2 ways. One of the first way is that you need a very smooth transition between your ground imagery and your aerial imagery. Let's say you have a copter, you can start taking the facade of a building, but then very importantly, after you do the facade, oblique facade, you need to take a lot of imagery between this oblique and a flight plan which would be more nadir, and then you can fly as a grid. If you do that nicely, then you can add everything in a single project and process it, and the software will do it alone. However, if this is not possible, and very often this is this is not very easy to do in practice, we would recommend to do one project fully oblique, either by ground or with a copter from the low altitude to process it. One project from nadir to process it independently, and then when you merge them together into software, you add manual Tiepoints between the 2 projects, and this will relatively help them to align one to each other. Another type of flight plans is, which happens quite often too, is to have double grids. So basically you fly one in a grid pattern, and then you do again the same grid. This is usually happening when you are limited by your camera or your UAV to a maximum amount of overlap because your UAV is flying too fast or your camera is too slow at taking pictures. This is an artificial way of adding more overlap. And this works pretty nicely. If you had the options between doing a single grid with more overlap or a double grid, we would recommend the single grid with more overlap. This was always going to give better results. But if you cannot give more overlap and your terrain is very difficult and you need more overlap, then you can do a second flight in the same at the same area. However, what's very important is to make sure that you don't do the same flight exact and that the images are not taken at the same position. If the images are taken at the same position, then you are not adding overlap. You're just adding more confusion to the software. So when you do that, we would recommend that the second grid is doing perpendicular, and that the second grid is shifted such as the points will be really adding more overlap than just adding more confusion. With that, I'll conclude the webinar. I'll conclude with the fact that you can always get a 1 free week trial of Pix4D Mapper on our website, and that this video will be downloadable on our website in a few days.